Today we will be discussing Astm C39, standard test method for compressive strength of cylindrical concrete specimens, and later the Astm C78 standard test method for flexural strength of concrete. The purpose of this report is to determine the compressive strength of cylindrical concrete specimens prepared by conducting experiments. Another objective is to determine the quality control of concrete proportioning, mixing, placing, and also the control for assessing the effectiveness of admixtures.
Introduction. Concrete's compressive strength determines whether the concrete placed in a structure can bear the weight of what's on top of it or if it will splinter into a million pieces and cause the structure to collapse. Concrete strength is highly variable and can change with many factors including the size, shape, and condition of the cylinder, the way it was batched, mixed, and transported from the concrete plant to the job site, the way it was molded in the field, and the temperature and moisture condition during the curing process. Lightweight concrete will differ in mix design and strength compared to regular concrete. Smaller samples may be able to handle less load than larger ones. Engineer can use strength test result to see if the concrete being poured fits with what it is being used for and meets their specification requirements. These results are their quality control for whole process of pouring concrete from batching to placement. So it is highly important for engineers to know how strong concrete is, and so construction material testing companies send their field technician to various construction site to make cylindrical samples out of the same concrete that is being poured. So these are the equipment for concrete strength testing. One of them is testing machine. The testing machine is powered by hydraulic fluid and uses a piston to lift the lower bearing block and push the cylinder into the upper bearing block, loading the cylinder with increasing weight until it ruptures. It is typically operated by a lever or several buttons to retract, hold, or advance the lower bearing block, and its result may be reported by a dial gauge or a digital readout. This is a sensitive piece of equipment and it must be regularly calibrated and maintained. Calipers, or ruler. Measuring the diameter of each cylinder is vital to the test result, as you will need to calculate the area of the cylinder to find the strength. Keeping a daily record of your cylinder diameter is recommended. No individual diameter on the same cylinder can vary by more than 2% or the sample is invalid. Carpenter's square. These are useful to check the perpendicularity of the cylinder's axis, making sure that the cylinder does not depart from perpendicularity by more than 0.5 degrees. It helps to get one that comes with a bubble level. Straight edge, 1/8 inch nail and 1/5 inch nail. This is used to check the plainness of the ends of the cylinder. You put the straight edge across the end of the cylinder and poke the nail at it to see if it goes underneath. So the 1/8 inch nail is used for capping and 1/5 inch nail is used for unbanded caps. So retaining rings. If you are using unbanded caps, these contain neoprene pads that help absorb the shock on the cylinder as it breaks and go over the ends of the cylinder. Make sure they are level when you place them on. If you work in a lab where these are exposed to the element and you don't want them to rust, regularly clean them with a wire brush and some WD-40.
The activities or procedures for this experiment are as follows. First, specimen must be kept moist. It should be tested while in moist condition. Measure the diameters of the specimen at right angles to each other. Wipe clean the upper and lower bearing blocks. Also clean the ends of the specimen. Place the specimen on the lower bearing block and align the axis of the specimen with the center of thrust of the upper bearing block. Verify that the load indicator is set to 0 before starting the test. Apply the load of 35 plus minus 7 psi per second continuously and without shock. Apply the load until the specimen fails or until it cracks. Record the maximum load carried by the specimen. Lastly, take note of the type of fracture pattern of the specimen.
Formulas. Compressive strength is equal to the maximum load the cylindrical concrete can endure before failure happens over the cross-sectional area of it, which is the area of a circle, that is equal to 1 over 4 pi d squared, where d is the average of its lower and upper cylindrical diameter.
For the data results, we have 5 concrete cylindrical specimen sample. First, the upper cylinder diameter measured 4.01 inches, and the lower cylinder diameter measured 3.99 inches, and the max load is 50,000 pounds, and the area was 12.57 inches squared, and the max load or the PSI is 3977.72. For the second sample, the upper cylinder diameter measured 3.89 inches, and the lower cylinder diameter measured 3.57 inches, and the max load is 50,000, and the area is 10.89 inches squared, and the max load we compute was 4,591.37 psi. The third concrete cylindrical specimen is the upper cylinder diameter measured 4.05 inches, and the lower cylinder diameter is 3.88 inches, and the max load is 50,000 pounds, and the area was 12.31 inches squared, and the PSI is 4,061.74. For the fourth one is 4.12 inches, and the lower cylinder diameter measured 3.89 inches, and the max load is 50,000 pounds, and the area was 12.81 inches squared, and the PSI was 3,903.20. And the last concrete cylindrical specimen was the upper cylinder diameter measured 3.75 inches, and the lower cylinder diameter measured 3.41 inches. And the max load is 50,000 pounds, and the area is 10.06 inches squared, and the PSI is 4,970.18 psi.
Computations. The area of the first cylindrical concrete, or A sub 1, is equal to 1/4 times pi times quantity 4.01 plus 3.99 all over 2 quantity squared. That will give us 12.57 inches squared. Using the same formula, we can get A sub 2 to A sub 5, that will give us the values of 10.89 inches squared, 12.31 inches squared, 12.81 inches squared, and 10.06 inches squared. Proceeding, we can now substitute the values of their cross-sectional area to the formula of compressive strength. Compressive strength of the first cylindrical concrete, or CF sub 1, is equal to 50,000 pounds over 12.57 inches squared. That will give us 3,977.72 pound per inches squared, or PSI. Following the same formula, CS sub 2 is equal to 4,591.37 PSI. CS sub 3 is equal to 4,061.74 PSI. CS sub 4 is equal to 3,903.20 PSI. And finally, CS sub 5 is equal to 4,970.18 PSI.
And for the drawings and figures, this is the compression test where the concrete cylindrical specimen being tested for compressive strength. The upper part is we call steel retainer, and followed by the pad, and the third one is the concrete cylinder or the sample specimen concrete. The next is lower pad, and the bottom is steel retainer. For the figure 2, we have kinematic of typical fracture patterns. We have different cylinder fracture types. The first type is reasonably well-formed cones on both ends, less than 1 inch or 25 mm, of cracking through cups. For the second type is well-formed cone on one end, vertical cracks running through cups, no well-defined cone on other end. For the third type is columnar vertical cracking through with both ends, no well-formed cones. For the fourth type is diagonal fracture with no cracking through ends, tapped with hammer to distinguish from type 1. For the fifth type is side fractures at top or bottom or occur commonly with unbounded gaps. For the last type is similar to type 5 but end of cylinder is pointed.
Okay. Common sources of error. No, since unfortunately we were not able to conduct the experiment personally, and as per advice ni Sir, what I'm going to present to you right now are those common sources of errors that we usually encounter when we're conducting experiment like this one. No, palagay ko naman lahat sa atin are familiar with these common sources of error because I'm sure all of us have already conducted series of experiments way back nung wala pang pandemic, no? Nung mga lower years natin sa chemistry and physics. So, before we proceed to the common sources of error, let's first understand these two types of errors, no? These two types of errors are categorized based on how it affects the result of the experiment, no, and how it affects the data that we obtained from the experiment. So those two types of errors are the random error and systematic errors. When we say random errors, it occurs due to chance. Now, it may be caused by slight fluctuations in an instrument, the environment, or the way a measurement is read that do not cause the same error every time. So it does not happen always. No? It does not happen all the time. And ang ibang tawag dito is accidental errors, since the sources of these errors are usually unknown. So as a result, it reduces the reliability of the result of the experiment. So since the error nga is is the result that we obtained from the experiment with random errors are erratic. So erratic ang result dito. While when we say systematic errors, it gives measurements that are usually consistently different from the true value in nature. It is often due to limitations of either the instruments or the procedure. So when we say naman systematic errors, the errors that we're committing are consistent, no, consistently happening all throughout the experiment. No, so but it is different from the true value. So it reduces, no, the accuracy of the result kasi meron ngang error. To further understand, no, the distinction between random and systematic errors, look at this illustration. So to further distinguish the difference between the two errors, so let's consider those red dots as the data that we obtained from the experiment. If you'll notice in the systematic error that the resulting data are in a grouping behavior. So meaning to say, ang data that nakukuha natin in the experiment with systematic error are precise. So though it's not accurate since sinasabi natin kanina, it gives different value from dun sa talagang true value that we're supposed to be obtained. Now, whereas dito sa random error, since the causes of errors are usually unknown and random, so yung resulting data that will be obtained from the experiment is also random and erratic nga. That's why sinasabi natin that experiments with random errors are usually it's not that much reliable. So, so those are the two types of errors, no, based on its effect, based on how it affects the result of the experiment. So let's proceed na dun sa talagang common sources of errors. So common sources of error, I have here I think 4, no, but it's not limited to this list. Let's start with instrumental error. So it happens when the instruments being used are inaccurate. So plain and simple. No, if the instrument that we're using is defective, gives an inaccurate result, so it is an example of instrumental error, like this one in our example. No? The weighing scale gives a negative mass, no, of an apple on a scale, which is wrong kasi wala namang negative mass. So that is an example of instrumental error. Next is environmental error. It happens when some factors in the environment, such as uncommon event, leads to an error. The environmental errors have different causes, including temperature, humidity, magnetic field, constantly vibrating Earth's surface, wind, and improper lighting. So here's an example of a common source, environmental error. The Geiger counter, that's the Geiger counter on the left, shows a normal radiation reading. Now, however, the Geiger counter on the right, when a cell phone is put near it, the radiation is read as greater than what it actually is because the cell phone is radiating RF waves, which disrupts the reading. So that's why one thing also that comes to mind when we say environmental error, yung binabanggit ng mga proof natin when we're conducting outdoor experiments such as yung measuring distances. Know that we should always consider the temperature and humidity when we're doing the experiment kasi it affects the measuring tape that we're using, no? Kaya ginagawa yan to avoid, no, to avoid the environmental error. So yon. Next is procedural error. It occurs when different procedures are used to answer the same question and provide slightly different answers. Now it happens, usually it happens when the procedure that we use in the experiment is not in conformity with the standard procedure na talagang dapat ginawa. So, example is if two people are rounding and one rounds up and the other rounds down, rounds, ulit. If two people are rounding and one rounds down and the other rounds up, nabulol pa. It's an example of procedural error. Okay. Next is a human error. No. So obviously we can expect a perfect experiment, no, since it is conducted by humans, which is not perfect. Well, so it is due to carelessness or to the limitations of human ability. There are two types of human error: the transcriptional error and estimation error. When we say transcriptional error, it occurs when data is recorded or written down incorrectly. So, dito papasok yung mga typographical error, yung mga maling lista. No, yung tama naman yung reading but the data that we recorded are wrong. So, when we say naman estimation error, it can occur when reading measurements on some instruments. For example, when reading a ruler, you may read The length of a pencil is being 11.4 centimeters, while your friend may read it as 11.3. So it's more of a one error in judgment, no, yung estimation error. So these errors are the most common sources of error, no, that we usually encounter when conducting experiments. But sabi ko nga, it is not limited to this list. So, meron pa. Hindi lang naisama siguro. So, in conclusion, C39 or C39M is the standard method of determining the compressive strength of a cylindrical specimen by applying actual compressive force to molded cylinders or cores at a rate which is within a prescribed range until failure occurs. The method should be done in accordance with other ASTM practices. The data obtained in the test method are being used as a basis for proper handling of concrete, such as concrete proportioning, mixing, placing operations, modifications, and improvements. So this concludes our presentation with regards to the topic of ASTM C39 or the standard method for testing the compressive strength of a cylindrical specimen. The next topic po will be the ASTM C78.
Good afternoon, everyone. For the next topic, we have the ASTM C78-02, or the standard test method for the flexural strength of concrete. For the first part of the report, we have our objectives. The first objective is this standard test method is utilized to be able to determine the flexural strength of a concrete through the use of a simple beam with third point loading. Next is to check whether the concrete design complies with the standard specifications. And lastly, to provide necessary information about the concrete that is useful in designing an engineering structure. For the second part of the report, we have our introduction. The flexural strength of a concrete, which is also called as modulus of rupture, refers to the evaluation of the tensile strength of unreinforced concrete done indirectly. Modulus of rupture can also be defined as the measure of the extreme fiber stresses when a member is subjected to bending. This is stated by Somya 2020. Furthermore, according to Hamakarim 2017, this test examines the ability of an unreinforced concrete beam or slab to resist the failure due to bending. It is particularly used in testing concrete for the construction of slabs and pavements. The specimens used in this test must be prepared and cured in accordance with test methods C42 or practices C31 or C192, which is stated in the ASTM C78-02 standard test method. In line with this, differences in the specimen size, preparation, moisture condition, curing, or where the concrete has been molded or sawed to size can give a variety of measured strengths. As this test can be used as a tool to measure the tensile strength of an unreinforced concrete, it can help in designing different structural components like beams and cantilevers that can confidently serve its purpose. Moreover, it can provide a parameter or standard in developing stronger and more durable construction components in the future. It ensures that the concretes being used are complying with the specifications and standards needed to have a safe and strong engineering structure.
Instruments used for ASTM C78. Megaforce Concrete Compression Tester. It is used to eliminate compressive and flexural strength errors because it maintains the specified ASTM rate in the whole process. and also increase the capacity of the compression testing machine. Indicator. It is used to conduct tests on concrete cylinders, cement cubes, and beams, and it is easier to measure their live and peak load or stress because of its easy-to-use interface, which greatly increases its efficiency. Expert 2600. This machine is mainly used for testing the material's strength, compression, tension, peel, and flexure.
What is flexural strength? Flexural strength is one measure of the tensile strength of concrete. It is a measure of unreinforced concrete beam or slab to resist failure in bending. Why test flexural strength? The designer of pavement used a theory based on flexural strength. Therefore, laboratory mix design based on flexural tests may be required or cement-used material content may be selected from the past experience to obtain the needed design MR. Standard test method for flexural strength of concrete using simple beam with third point loading.
This video demonstrates a molded 6 by 6 inch beam being broken to determine its flexural strength.
Procedure. Step 1. Flexural test of moist cured specimen shall be as soon as practical after removal from moist storage. Surface drying of this specimen results in a reduction in the measured flexural strength. Step 2. When using molded specimen, turn the test specimen on its side with respect to its position as molded and center it on the support blocks.
Mark the beam to help with centering in the machine. One way of doing this is locating the middle of the beam and marking it. From the middle, measure 3 inches on either side and make another mark. Next, measure 6 inches from both of those marks to make the last mark. For this beam, the span length is 18 inches.
Load the specimen continuously and without shock. The load shall be applied at a constant rate to the breaking point.
Apply approximately 3 to 6% of the estimated maximum load to the beam. Check for gaps between the specimen and the blocks. If there are no gaps less than 0.004 inches, then no adjustments need to be made. If the gap is between 0.004 inches and 0.015 inches, then you must cap, grind, or shim the beam. If a gap is greater than 0.015 inches, it must be corrected by capping or grinding the beam. Check for gaps greater than 0.004 inches over a length of at least 1 inch. Check this for all blocks. In this example, there is a gap greater than 0.004 inches over a length of 1 inch. Next, check for gaps greater than 0.015 inches. Check this for all blocks. There are none, which means that we can cap, grind, or shim this beam. Shims should have a thickness of 0.25 inches, a width of 1 to 2 inches, and should extend the full width of the beam. Insert the leather shims between the specimen and the blocks. Load the beam at a constant rate of 125 to 175 psi per minute until rupture occurs. Record the maximum load. Remove the beam. For this beam, the fracture occurred in the middle third of the tension face. The tension face is the bottom of the beam as loaded in the machine. Choose one of the beam pieces and measure the width and depth. To measure, turn the beam so that the tension face is facing upward or downward. Record 3 width measurements by taking a measurement on each edge and one in the middle as shown. Then, record 3 depth measurements by taking a measurement on each edge and one in the middle as shown. Record each reading to the nearest 0.05 inches. Calculate the modulus of rupture based on the location of the fracture on the tension face. If the fracture occurred outside the middle third by more than 5%, discard the test results. Report the modulus of rupture to the nearest 5 psi.
The first formula is R is equals to PL divided by BD squared, where R is the modulus of rupture, P is the maximum applied load, L is the span length, B is the average width of specimen, and D is the average depth of the specimen. This formula is used when the specimen broke within the middle third of the span length. The second formula is R is equals to 3PA divided by BD squared, where A is the distance between the line of fracture and the nearest support, measured along the center line from the bottom of the beam. This formula is used when the formula broke outside the middle third of the span length by not more than 5% of the span length. To get the approximate relationship between modulus of rupture and compressive strength, we use the formula compressive strength is equals to modulus of rupture squared divided by 100.
To determine the dimension of the specimen cross-section for use in calculating modulus of rupture, take measurement across one of the fractured faces after testing. For each dimension, take one measurement at each edge and one at the center of the cross-section. Use the 3 measurement for each direction to determine the average width and the average depth. Take all the measurement to the nearest 0.05 inches. If the fracture occurs at a cup section, include the cup thickness in the measurement.
For computations, we have solved the modulus of rupture using the formula R is equal to PL over BD squared that indicates the fracture initiates in the tension surface within the middle third of the span length. With that concept, we researched more about computations with regards to the standard test method for flexural strength of concrete using simple with third point loading. And we found an example with this given that has a P or maximum applied load of 7,700 pounds, L or span length of 18 inches, B or average width of the specimen, the fracture having 6.3 inches, and D or average depth of specimen at the fracture having 6 inches. Note that these computations were calculated after the test is completed. Using the formula, we have calculated that R, or the modulus of rupture, is equal to 638.47 psi. Here in the next slide, you can see a table showing all the tests with different loads applied to it and its result of modulus of rupture, which is the ability of a concrete to withstand its capability to bend. And it is defined as the stress in a material just before it yields in a flexure test. We have here the description of test specimens, which has a position of 6 by 6 by 21 inches and the distance it has between supports. We have here the number of days it was cured, its average depth and width at the fracture and the location of it. As you can see, all of them has a location of fracture at the middle third. which has been solved by the previous formula presented for modulus of rupture, which is R is equal to PL over BD squared. But at specimen number 5, you can see that the location at fracture is 3.9 inches from the support. That's why we will be using the formula that if fracture occurs in the tension surface outside of the middle third of the span length by not more than 5% of the span length, which is the formula R is equal to 3PA over BD squared. A is the average distance between line of fracture and the nearest support measured on the tension surface of the beam, and solving by that formula gives us 420.398 psi, but it was disregarded because it was not within the 5% criterion.
In this experiment, we will be just using two things, which is a specimen or a block and a UTM. In the first figure, that's the UTM, and in the second figure, the specimen is inside the UTM, and the load applying blocks are already aligned with the measurement of the specimen. Concrete is not moist. When concrete is not moist, it is prone to shrinkage. So to ensure stability in size all throughout the experiment, the concrete should be kept moist. The loading on the beam is not uniformly distributed. The load that will be applied on the concrete must be uniformly distributed to successfully determine the strength and integrity of the concrete, and the rupture would occur on the middle of the specimen. The specimen should be equally divided into three, with a specific allowance on both ends, which should also be the same in size. Failure to do so would cause inaccurate measurement of the strength of the beam. Too much on either end would cause unequal stress capacity on the beam once the load is applied. Gaps are greater than 0.0004 inches between the specimen and the block. The gaps between the load applying block and the specimen should be less than 0.0004 inches so that each load applying block exerts the same amount of stress. Anything beyond that should be filled. The applied stress per minute exceeds 175 psi per minute. The suggested stress per minute should be between 125 to 175 psi per minute and applied constantly.
Now, arriving at our conclusion, Astm C78 is for flexural tests of concrete used in slab and floor construction with a third point bending device. This testing method is used to measure the flexural strength of the preparations and curing specimens with accordance to the following standard test methods, which are C42 or C42M, C31 or C31M, C192, and C192M standard test methods. The results will be calculated and shown as a rupture modulus. For the same sample size, if the sample preparation, curing procedure, moisture at the time of the test is different, or if the beam is molded or sawed to size, then the strength found will change. As the specimen size lowers, the measured rupture modulus usually increases, as shown in this figure in our presentation. The outcome of this test method may be used to determine compliance with specifications or as a basis for mixture proportioning, evaluating uniformity or mixing, and checking placement operations by using sawed beams. Now, it is used primarily in testing concrete for the construction of slabs and pavements. For identical test specimens, the modulus of rupture obtained by this test method will, on average, be lower than that obtained by test methods C293 or C293M test standards. That would be all, and thank you for listening. We are Group 3.